Hi Stats class, it's Miss O'Neill and I am getting ready to show you guys some notes about proportions. Today is Thursday. It's going to be the 23rd of April, which seems to be flying by. Now, when we first started talking about proportions, you had a little bit of an example in your assignment from Tuesday where it reviewed your unit rates from last week, okay? One of the examples that they had shown was this idea of 108 students trying to be split up into 4 classes or 4 groups, okay? Now, obviously, if I want to change this fraction, it does matter how I change it. You can always make something become larger or smaller, and it depends on your need. If I need to know how many kids are in each one of my groups, I need to get the bottom number to become 1. That's our example of the unit rate that you guys had practiced last week. Our goal of taking a fraction and making its denominator, its bottom number, into 1. So this raises the question, if I take the bottom number and I've made it smaller, that top number has to become smaller as well. But we have to be very specific in how we change it. It's got to stay equal. So if I changed 4 to 1, we have to think about how do I get 108 to change into an equal piece that still makes this fraction the same as that. Last week, we talked about the idea of division, all right? Taking that little fraction, which means to divide, and using that to help us figure out our answer. If we did 108 divided by 4, your calculator would say 27. So we can say there are 27 students in one group. Another way we could write that is 27 to 1. Okay? Now, one of the things that proportions brings up is this idea of looking at these two fractions and saying, are they equal? At first glance, some kids are going to look at this and say, obviously not. They're not the same numbers. But that's where you have to be careful. I'm looking at the entire fraction itself. If I was to type this fraction into my calculator, it would say 27. If I was to type 27 divided by 1 in my calculator, it would also say 27. Is 27 equal to 27? Yes, it is. Then what does that mean about the fractions? They are also equal. So a proportion is telling us that even though the fraction may not look identical when we first glance at it, their makeup, how they are related, is actually considered to be equal as well. And that's what we're going to try to focus in on. Some real life examples of proportions that you guys should be kind of connecting with. First example that I always think of is baking. Any kind of recipe, if you're cooking, you got to think about it. Your goal with certain recipes is to decide, am I cooking for a lot of people? Then I might need to make my recipes get larger. If I'm cooking for just me, I might need to make them go smaller. But if you're changing a recipe, whether it to become larger or smaller, greater or less, the big thing you have to make sure is that you're not changing the proportions. I don't want to accidentally have way more garlic powder in my food than I'm supposed to, just like I don't want to end up with way more oil in my recipe than I should have. It all is about keeping a balance, keeping your relationships equal. So, keeping that in mind, your notes today are going to talk about this idea of proportional relationships, and that is our focus on us being able to figure out proportional versus non-proportional. So if we're keeping that in mind, if the ratios or rates of two quantities are equal, which we talked in class before, that means they are the same, then the quantities are proportional. That was the example we had just looked at. So let's think about the complete opposite of that. If the ratios or the rates of the two quantities are not equal, they are not the same, then we call those quantities non-proportional. Okay? So why does this matter? Well, let's take a look at our example. Eric and Lucy ran 20 minutes each on the treadmill at the gym. The table below shows the number of calories each has burned after 5-minute intervals. Complete each table and determine the type of relationship. So, if we are taking a look, Eric, 5 minutes have gone by, he's burned 70 calories. 10 minutes have gone by, he's burned 140 calories, and so on. Looking over at Lucy, in 5 minutes, she's burned 45 calories. If we're comparing the two, we would say Lucy looks like she's going down a lot quicker. In 10 minutes, we have 90 calories. 15 minutes, we have 120. Now, what we're trying to figure out is if Eric is running at a proportional rate, meaning is his burning of calories in his time equal all the way down? In other words, it's like thinking about the idea of pace. Is Eric running at the same rate over and over again? Is Lucy running at the same rate over and over again? So how do we figure this out? Well, you need to think about the idea of how you're going to set up your fraction. Which one sounds more appropriate? Calories per minute or minute per calories? We burn calories per minute. Time usually will always end up on the bottom. So our goal here is to work with division. If we did 70 divided by 5, we need to figure out what that would be. So breaking out that calculator, 70 divided by 5 is 14. So Eric has 14 calories per 1 minute. If he is proportional, what does the next one have to be? Let's check. 140 divided by 10. That's 14 again. So many of you are going to look at this and you're going to say, all right, this person's proportional. We're done. We're moving on. Got to be careful. I like to trick you. So you have to check the entire table. All pieces must be examined. So if I continue, 210 divided by 15, 280 divided by 20. In order for Eric to be proportional, I should be able to type in each one. That's looking real good. Last one matters. Oop. It'd be nice if I put in the correct one. Always double check your calculator work. There we go. So, looking at Eric, what is he? He's proportional. But this is looking for a reason why. It wants us to explain. So what am I seeing happening in Eric's example that tells us we are proportional? Right here. Every rate is equal. Okay. So the calories burned by Eric is proportional to the time because every rate is equal. Looking at our example for Lucy, take a moment, remind yourself you're doing calories first, divided by time. And I want you to determine what is Lucy. So if we're looking, first one was 9 calories per minute. 90 divided by 10 gave us 9, looking real good. 120 divided by 15 gives us 8. And 180, divided by 20 is 9. So if 3 out of the numbers end up being 9 and we only have one different one, can it still count as proportional? Well, that's a very easy way of asking. Are they all equal? If you cannot say yes, this is a no. This is not proportional. So Lucy is non-proportional. to the time because her rates are not equal. They're not the same. She is not burning the same amount of calories every single minute. Okay? So, now that we've got a little bit of practice and we can ask ourselves whether we can say, yes, it is proportional or no, it's not, let's put that to some practice. In many examples, what you're going to see is information that's going to ask you to determine whether the quantities in each table represent a proportional relationship. If yes, give the constant rate. That's another way of saying give me the same rate that you see that repeats. So if we look back at our example with Eric, he was, yes, proportional. His constant rate, the rate that repeats, was 14 calories per minute. So let's take a look at our first example. One of the biggest things that we do have to be careful with is the idea of how we're setting up our fraction. If we're taking a look at our information, we usually will use this bottom of a fraction and we would put that on top of the proportion. So it would be students to buses. Okay? In science class, you have been talking a lot about the idea of an independent variable and a dependent variable. The number of buses, X, decides how many students are going to be on it, Y, or how many students can come along. So in this case, the independent one is the buses. I can control how many buses I can have for a field trip. The number of students decides how many I can take on that field trip. So now that we have that set up and we understand how we're going to go and do our division example, we're going to try it. We're going to do 24 divided by 1. That gives us 24. 45 divided by 2. That gives us 22.5. 78 divided by 3. That is 26. And 100 divided by 4. That's 25. Can I say, yes, this is proportional, or no, it's not? Nope. None of these are the same. Okay, I could have actually stopped right here when I realized that these two numbers were not the matching pieces. They need to be the same. They need to repeat over and over again. So remember, on number 2, we're going to take the money, we're going to divide by the hours. So 36 divided by 4 gives me 9. 72 divided by 8 gives me 9. When I see them match, I have to continue until I find it that it doesn't match. 90 divided by 10 is 9, and 135 divided by 15 is still 9. If they are all the same number, this is going to be a yes. This is a proportional relationship. And the constant rate, the rate that repeats, is the 9. And we're going to call that $9 per 1 hour. Okay. So one more example, and then I'm going to have you go ahead and try and see if you can get this one. Let's take a look at number 5. So again, our choices are number of candy bars and cost. Setting up this proportion, we're going to put money on top, and we're going to put the number of candy bars on the bottom. Go ahead and see if this is, yes, proportional, and then tell me it's constant rate, or no, it's not proportional. 4 divided by 5. Your calculator will end up spitting out 0.8. 8 divided by 10. 16 divided by 20. And 28 divided by 35. You should have said, yes, this is proportional. And its constant rate, now trying to go back to here, we're knowing that this is supposed to represent money. So 0.8 is another way of saying 80 cents per one candy bar. So 80 cents for me to get a chocolate candy bar. So keeping this in mind, why does this matter? Why would I need to know if the relationship that is being presented to me is actually proportional? Well, we can use it. Real life scenarios down here. Because I know what my constant rate is, I can use it over and over and over again. For example, on number 7, it tells us that Ben earns $8.50 per hour bagging groceries at the grocery store. If I know how much Ben is earning in 1 hour, that's not necessarily going to help me figure out a final paycheck if all I know is that in 1 hour he's got $8.50. But you can actually use that information. Think about it. If I'm setting that up, $8.50 per means the division sign. And remember, if you have a unit rate, the bottom is always going to be 1 hour. This is an example of us trying to change our proportion by increasing it. Instead of me working 1 hour, Ben's worked 4. If I make the 1 hour go up, I have to make my amount go up. So we have to think about, if I had to divide to find out the proportion, the unit rate, what am I going to do that is the opposite to get it to go up? Multiply. Awesome. So in here, we're going to show multiplication by using a little bit of parentheses. We're going to do $8.50 times 4. If you're using a calculator, you can do 8.50 times the 4. And if you have a graphing calculator, they have wonderful little parentheses above the 8 and the 9. So you can also practice using parentheses. And as you can tell, it gives you the same kind of answer because the calculator assumes parentheses means to multiply. So Ben worked 4 hours. He's getting $34. Okay? Well, let's say he's worked 8 hours. You see how we're jumping here? We have 2 choices. We can stay at 34 and add $8.50, another $8.50, another $8.50, another $8.50. By that time, we'd have 4 extra more hours added to our payment, and we would be up to 8. But that takes too long. So your shortcut is to continue taking how many hours you worked and multiplying by your unit rate. $8.50. Doesn't matter the order. When you're multiplying, you can switch it, still gives you the same answer. That's going to be $68. Now we're jumping to 10. 10 times $8.50 is going to end up giving you $85. And then 14 times $8.50, that's going to give you $119. If I did this right, I should be able to do 34 divided by 4, get $8.50. 68 divided by 8, get $8.50. 85 divided by 10, $8.50. 119 divided by 14, $8.50. That repeating rate needs to stay constant, meaning it needs to repeat, because of the fact that we use it for every single relationship. It's the one thing that keeps this being all tied together as a story. If I'm jumping to question number 8, the wide receiver can run 9 yards per second. Okay, that is our unit rate. So in 1 second, how far did they go? Well, in 1 second, they went 9 yards. We know that automatically. They told us. If you weren't 100% sure and you wanted to double check your math, you could take 1 and times it by 9. Make my seconds go up. yards have to go up. That keeps our relationship the same. So 9 times 3 would give us 27 yards. 9 times 6, 54 yards. 9 times 10, 90. We're going to jump down a little bit and we're going to look at question number 10. In this one, it says the real estate office sells 7 homes per month. In that first sentence, this matters. This is your unit rate. I know in 1 month, I'm going to have 7 homes sold. Sweet. We're going to complete the chart. And then we're going to determine how many homes they sell in 2 years. This is a 2-part question. So part 1 is to complete the chart, and part 2 is to determine how many homes they sell in 2 years. So if we're looking at our table and we see it's 2, 5, 8, and 10, how do I calculate the number of houses sold based off of this one piece of information? Go ahead and multiply by the unit rate. We end up with 14. 7 times 5, 35. 7 times 8, 56. And 7 times 10 is 70. So, if I reread my directions, I've completed the chart. Check. I'm not completely done though. Last part, determine how many homes they sell in 2 years. This is what they want us to find. If I give you 2 years, how many homes have I sold? Here's the catch. Look at your table. Months, homes sold. I need to know this number. That's my unknown, my question. This, they have given to us, but they've tried to trick us. If we look back at our table, this represents months, but they're giving us 2 years. Can I just put a 2 in here and say that counts? No. Because if you put a 2, you're saying 2 months, and we already got that answer. That's not going to be correct. So we have to think about that idea of 2 years. If I have 1 year, that's 24. I'm sorry, that's not 24. That is 12. I'll rewrite it. 12 months. Here's a perfect example of us trying to change a relationship. If 1 year is 12 months, we need it to become 2 years. So if I go from 1 to 2, 12 would have to jump up to 24. So if we're looking at these two, I cannot use 2 years because it doesn't relate to my story. I have to use 24. So we have 24 months in here. To get our answer, we times it by 7, and 24 times 7 is 168 homes. That's a lot of homes. Okay? And there you have it. Proportions. Big idea here is that you need to have a repeating constant rate to be considered a proportion. You have to remain the same and continue to relate to the previous story.